Hi, let's talk about the sample linear correlation coefficient in the context of X and Y. We're not in a time series setting yet, but this discussion will help us when we start talking about autocovariance and autocorrelation in the time series setting. So we first need a definition. So we'll say R, the sample linear correlation coefficient, we'll say between X and Y is equal to, and that is the sum of Xi minus X bar times yi minus y bar divided by our sample size minus 1 in minus 1 sigma hat x, that's the sample standard deviation of the x's, and the sample standard deviation of the y's. And that is a number between 1 and negative 1 that helps us measure the magnitude of a linear correlation, be it positive or negative, between X and Y. So let's see how that works. That's kind of what we want to look at here. Is we know intuitively or through practice that if we have some variables and these are X and these are Y's and these X's and Y's, we take a sample and they turn out something like this, that is evidence of a positive linear correlation. And so R should be positive here. But what do we actually mean by that? How does R become positive? How does it become bigger than 0 and between 1? So what I'm going to do here is we'll talk about X bar. So I've got all these points have X's. Each of these is an XY pair, right? Kind of remind us of that as being right here. So each of those is an XY pair. And so all of this has a very small x, that has a very big X. Those x's are all relatively in between those two. So if I looked at all of the x's, just looking from there to there, all those x's in there, I'd say that X bar is right about, say, there. So we'll say X bar is right about there. And we'll do the same thing with the y's. So with the y's, we say, oh, this one has a low y, and that one has a big y. All these points have y values. These are all in the middle somewhere in the middle y's. But I'd say that the y's have a y bar right about there. Great. And so now we're in a position to see how R, the sample linear correlation coefficient of Rxy, becomes positive. And again, this will help motivate us when we talk about autocorrelation, autocovariance in the time series setting. So checking it out over here, look at all these points. Let's just look at the x's. So the x's here, this has a relatively big x, right? That point's x would be right about there. That point's x would be right about there. Those are all bigger than X bar. So all of these points, if I do Xi minus X bar, the Xi is big and the X bar is small, then I've got Xi minus X bar, and I'll put out here is positive. So let's do the same thing for the y's. Notice these are all relatively big y's. These y's are all up here. That y is there, that y is there, and y bar is down here. So yi minus y bar, yi for this point minus y bar for that point, will be positive. Also be positive. Y minus y bar will be positive. And all the points in this upper right hand quadrant will have xi minus x bar positive and yi minus y bar positive. Great. So let's go down here in this quadrant, the lower left quadrant. So let's check all these out. These all have low x's. Look, these x low, 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 low. All those x's for these points in this lower quadrant are less than x bar. So xi minus x bar here, for all of these points, xi minus x bar will be negative. Right? That's low x minus bigger x bar. Xi minus x bar will be negative. And notice that this one is really far away from x bar. So that'll be a big negative number. This one, now look at that point right there, is almost right on x bar. So xi minus x bar will really be close to 0. It's going to be important here in a minute. Again, with these points up here, this x is relatively really big, and that x bar is way over here. So that'll be a big positive number, and that'll be a relatively small positive number. So now let's look at some of the other quadrants. How about that point? We only have one point here, and it's almost on y bar. Right? Its y point is almost on y bar, but it's not quite there. It's a little bigger, and the x is a little bit smaller, right? That x is right here, and so x is smaller than x bar. So this xi minus x bar, it's a minus sign, xi minus x bar will be negative, and that y is bigger than that y bar, just barely. So yi minus y bar will be positive. But that's a relatively small number. So in this one, that'll be so that will be negative for that point, and that will be positive. And we'll multiply those here in a second. In fact, so let's do this one here. We've got, we'll say that's 1 point. There's another point. This x is bigger than that x bar. This point's x is bigger than that x bar. Relatively very small though, right? Much smaller in magnitude. But these will all have xi minus x bar will be positive. And all their y's are lower than y bar though, right? That one's almost on y bar. That one's almost 0, but it's a little bit negative because that's going to be a small y minus a bigger y bar. That's a smaller y minus a bigger y bar. So these are yi minus y bar. Those will all be negative, but relatively very small. And that one relatively small compared to the rest. So when we add all these up, we're going to add the cross products. For all of these points, it's going to be positive times a positive. For all these points, 1, 2, 3, 4, 5, 6, 7, 8 points, that'll be 8 numbers added together, and they will all be positive, because that'll be positive times a positive is a positive. So that'll be 8 positive numbers added together. This number will be relatively large positive. This number will be close to 0, but still positive. Let's look at these. 1, 2, 3, 4, 5, 6, 7, 8. It's another 8 points, but they're all negative. I didn't write the y's down here. What are the y's? The y's are small and the y bar is big. So this would be yi minus y bar negative. Aha. Well, all of these points, for this point here, that'll be a negative times a negative times a negative is a positive. So these will all contribute to this numerator. It'll be the sum of 8 positive numbers, some of them big, and the sum of another 8 positive numbers, some of them big. Now, what about these points? Because this point will get added in there too. And this point has a negative this and a positive that. So that'll be a negative contribution to this sum, but it'll be, it's almost 0, right? That yi minus y bar is almost 0. So that point will be negative, but it'll be very close to 0. It'll be overcome by these other 16 positive numbers. And what about this? We said there were 2 numbers down here. These both have positive xi minus x bars and negative yi minus y bars. So those 2 points will have negative contributions to that sum, but very small. That one's almost 0, so negative but very small. And that one's relatively close to 0, relatively smaller than these other 16 positive numbers. So you have 16 positive numbers plus 3 negative numbers that are really small. So this one here will be overwhelmingly positive, which makes sense. We know that that's related to a positive correlation, and sure enough, the sample linear correlation coefficient will be positive because of what we mentioned here. Note that sigma x and sigma y are standard deviations. They're always positive, right? By definition, those are positive. N has to be a positive sample size, so that's positive. The numerator is always positive, and so this works out that way. So let's do one more. We'll go a little quicker here because we're going to look at what happens if we have this situation. Well, we know that that's a negative correlation, but let's make sure that makes sense with our intuition and our kind of mental exercise that we're doing up here. So we've got those. Now, if I look, that's a small x, that's a big X, that's a whole bunch of in-between x's. I'll say that x bar looks right about there. There's big Y, there's small y, there's a bunch of y's in between. I'll say that y bar is right about there. I might have underdone that, so good thing I have a pink marker, so I can cheat a little bit, balance those x's out. Okay, maybe that looks like a decent representation of x bar and y bar. So let's do our counting again. What about the sample linear correlation coefficient? We know that should be negative. We've already done the math, right? All these points here have xi minus x bar negative and yi minus y bar positive, right? All those y's are bigger than y bar. All those x's are smaller than x bar. We'll have that. So that's really far away, and that's really far away. That's going to be a big negative number up here because this is negative times a positive. Negative times positive will be negative. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 negative numbers, these being really big negative numbers and those being close to 0 but still negative. Now, what about these? We'll skip those for a second. Come down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's 13. That's 13 numbers. Let's see what there are. We already did the math here. Those all have big x's relative to x bar. So that's xi minus x bar, which is positive, but all of them have relatively small y's. So those y's are smaller than y bar, so it'll be yi minus y bar for all of those will be negative. And so all of those points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, all 13 of those points will be positive times a negative will contribute negative. These will be very large negative numbers, relatively speaking. Those will be close to 0, but still negative. So we'll have that 13 plus, what did I say that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 numbers. That's 23 negative numbers in the numerator being added together. We do have these two, right? Remember, those are big X's and big Y's. So those are xi minus x bar positive and yi minus y bar positive. But those are all, look at how small, right? That yi minus, or sorry, that xi minus x bar, that'll be relatively really small. This is relative to some of these big points. Those are relatively small. So it's going to be about 23 negative numbers, that some of them are really big negative, plus 1, 2 positive numbers, which those magnitudes would be relatively small. That overall sum is going to be overwhelmingly negative, which matches our intuition. We knew that that was a negative evidence of a negative relationship to begin with. So that is how the graphics, how the plots and the actual numerical sample linear correlation coefficient come to match. And that will be really crucial when we talk about autocovariance and autocorrelation. Nice work.